In this video, I want to talk about matrix multiplication. And to be honest, I almost didn't make a video about matrix multiplication because there are so many resources on the internet that will tell you how to multiply two matrices. We've in fact already seen it. If you've watched the 3 blue, 1 brown video about matrix multiplication as composition, he talks about how we can think of matrix multiplication in terms of a series of vector times matrix multiplications. If you haven't watched that video yet, I recommend watching it before this video because I'm assuming that you've already seen that video. Why did I make this video then? Well, there's two things I want to do. One is to present some really important properties of matrix multiplication along with what I call non-properties, things that are not true of matrix multiplication that are true in lots of other situations, like for instance, properties that the real numbers have, but multiplication of matrices do not. And I also wanted to go through an example of matrix multiplication and present how I like to do the calculation by hand. What I'm going to do in that calculation is equivalent mathematically to what was done in the 3 blue, 1 brown video, but the way I set it up, I think makes it easier to do the calculation and makes it so there's less to keep track of. There are lots of other people who do it the same way. It's not something I made up, but I think it is a good way to think about matrix multiplication so that you're not making mistakes and trying to figure out what the next step is as you work through it. Okay, let's start with some properties of matrix multiplication. The first property is really just a statement about what matrix multiplication is. That is, when we can do it. If we have two matrices, it makes sense to multiply them if the number of columns of A is equal to the number of rows of B. If that's true, we can multiply the matrices. If that's not true, we cannot multiply the two matrices. The next property is, again, not really so much a property, but a statement about why are we doing this, right? We didn't just make up matrix multiplication so that linear algebra students would have more work to do. The whole idea here is that matrices represent linear transformations. So if A is the matrix of T and B is the matrix of S, we can compose linear transformations if the dimensions of the spaces line up. So if we can compose T and S, then A times B is the matrix of this new linear transformation. A composition of two linear transformations is again a linear transformation, and it has a matrix. Which matrix? It's A times B. Again, the 3 blue, 1 brown video goes into this and explains why this is true. At the end of this video, I'll have a little section where I revisit this that you can watch if you want to see it again, or you want to see my explanation for why this makes sense, but I'm going to save that until the end in case you don't want to watch that part. All right, now let's get into some really just straightforward properties. Matrix multiplication is associative. If we can multiply three matrices, it doesn't matter whether we multiply the first two and then multiply that by the third, or we multiply the the last two, and then multiply that by the first, which is really nice. It means that if we're multiplying a product of three matrices, we don't have to think about what order we have to multiply them in. We don't even need parentheses, right? We could just write this as A, B, C. Another nice property is that matrices are distributive. We have a way of adding matrices and we have a way of multiplying them, and multiplication distributes over addition. Now, this might look weird the way I've written this. Usually you wouldn't write down two distributive properties, but we actually need both of these because, as we'll see later, matrix multiplication is not commutative. There's also an identity matrix for every dimension, and we'll either write this as I sub n if we want to make clear what dimension we're talking about, or we'll write it as I if in context it's clear what the dimension has to be. So as an example, the three-dimensional identity matrix is this, I sub 3. And in general, identity matrices are of this form. We have ones on the diagonal and zeros everywhere else. What's special about this? Why do we call it an identity matrix? Well, anything we call an identity should satisfy an identity property. And the property is that if we multiply a matrix on the left by the identity, or we multiply on the right by the identity, we always get the matrix that we started with. Now, there's a detail here that I didn't write down, but is worth pointing out. These are not necessarily the same thing. So what I've written here is very sloppy, right? So if we're multiplying A on the left by an identity, that means that this size of this is the number of rows of A. Otherwise, it wouldn't make sense. And similarly, if we're multiplying on the right, the size of this identity is the number of columns of A. And so we're kind of sloppy with our notation because we don't want to keep writing things down. But when I say that it's often clear from context, what I'm saying is that if we can multiply by the identity on the left, it's because this has the proper dimensions. And so that is to say, even though I haven't specified the dimensions of this identity matrix, it's clear from context that the dimensions have to just be the number of rows of A. Otherwise, it wouldn't make sense to multiply here. All right, let's look at some non-properties. And it's weird to list things that aren't true, right? Lots of things aren't true. I want to list some things that you might think were true just because they're true of the real numbers, but they aren't true for matrices. And the most important one is that matrix multiplication is not usually commutative. You generally can't assume that A times B and B times A are equal. In fact, usually if you can multiply A times B, you can't multiply B times A, right? The dimensions can line up in one direction, number of columns of A equals number of rows of B. That doesn't mean that the number of columns of B will equal the number of rows of A. So usually we can't even do this, but even if we can, right? Even if these are both square matrices and we can multiply them in either order, we don't usually expect to get the same thing. This was why I needed two distributive properties, because putting the distribution from the right is not really the same as putting the distribution from the left. What else? This is a property that you might not think of, but you could make this mistake pretty easily. If we're dealing with real numbers and they multiply to 0, and here the 0 means the all zeros matrix, right? With real numbers, if things multiply to 0, then one of them is 0. But that's not true with matrices. I'm not going to write down an example, but they're not hard to come up with. Matrices have what are known as zero divisors. It's possible to multiply two non-zero things and get 0. So we shouldn't assume that. And along a similar line, if we know that A times a matrix is the same as B times a matrix, if these were real numbers, either that second number is 0 or the first two numbers are equal. But that's not true of matrices. And there are tons of, as I said, listing things that aren't true. There's an infinite list, right? And you could come up with all these things that aren't true. But hopefully these non-properties lead you to think twice anytime you try to apply a property that you know to be true of, let's say, the real numbers to matrices. You should always be skeptical that what you know about the real numbers translates to matrices, because whereas a lot of things do, associativity, distributivity, a lot of things don't, like commutativity, and this kind of cancellation property. That was properties. Those were the main properties and non-properties I wanted to cover. Now let's look at an example. Oh, my example's not here yet. I was confused as to where it went. All right, so here's an example, multiplying two matrices. And I guess I don't know what happened to my last number. I want to multiply these two matrices. And I can do that, right? Because I have 4 columns in the first matrix and 4 rows in the second matrix. And in the 3 blue 1 brown video, they present this as saying, look, what we do is we take this vector and multiply it by the matrix, and that gives us the first column of the product matrix. And then we take the second vector and multiply by this matrix, and that gives us the second column of the product matrix. The problem with this, there's nothing wrong with it. It gives you a right answer, and it works exactly the same as what I'm going to do. What I'm going to do doesn't even really save computations. The problem with looking at it that way is you're calculating entire columns at once. I like to do this calculating each entry at once. And so I'm going to copy this and move things around a little bit. And what I'm going to do, I think that just copied. What I'm going to do is the same sort of thing that I did with matrix times vector. So the first thing I'm going to do to multiply these is, let's get rid of this little dot because I don't want that there. is I want to change the positions of these matrices relative to each other. Because I want to view this as we'll see, that the position of these matrices is telling me something about how to calculate the entries. So I'm going to end up with a 3 by 2 matrix. When we multiply two matrices, we need columns of the first to equal rows of the second, and then the resulting matrix has the same number of rows as the first, so 3, and the same number of columns as the second, so 2. And how do I do this? The way I look at this is that each row of this matrix points us to a row, and each column of this matrix points us to a column. And so these two combine to tell me this entry. For instance, this column of the second matrix and this row of the first matrix combine to tell us this entry. They all point to an entry. And in what way do we calculate those? Well, we take what's known as the dot product. So if I want to find the first entry, and so right now I'm going to try to find this first entry right here. And so in doing so, I'm going to use the column above it and the row next to it, and I'm going to take their dot product, which means that the way I calculate this is I do 3 times 3 plus, or let's do it in order, 3 times 3, it doesn't matter, but plus 5 times 6 plus negative 2 times 4 plus 7 times 0. So let me write that out. 3 times 3 plus 5 times 6 plus negative 2 times 4 plus 7 times 0. And when I add this up, I get 9 plus 30 is 39, minus 8 is 31, plus 0 is 31. And so this is that top left entry of the matrix. Advantage to doing it like this, to me, is that all of your computations can be done on the side, right? Rather than having some long sequence of computations, or even better, they can just be done in your head as long as you're not making mistakes. I often find myself making mistakes when I teach in person. I often will make mistakes on the board. When I make videos, I'll make mistakes and have to, edit my video, or I just won't. I'll just fix it. But let's see what I mean. If I'm trying to find this entry here, now I want this column and this row because they point to this entry. And so 3 times 1 is 3. 5 times negative 7 is negative 35. So now we're at negative 32. Negative 2 and 12 is negative 24. Negative 32 and negative 24 is negative 56. Negative 56 and 21 is negative 35. So I just found this entry in my head. Again, it can be risky, but this is nice, right? If you can make those calculations in your head, then you can do it really quickly, or even better, maybe you're just typing them into a calculator, right? But you're not writing down all of this extra stuff. All right, so let's finish this up. And what I'd recommend to anyone who's watching this, who's trying to kind of get this down, pause the video, finish the calculation of all these entries of the matrix, and confirm that what you get is what I get. And then you'll know that you did it right. Okay, so for this entry, we're working with this column and this row. 3 times 6 is 18, plus 0 is still 18, plus 4 is 22, plus 0 is still 22. 6 times 1 is 6, plus 0 is still 6, plus 12 is 18, minus 3 is 15. Now we're going here. 10 times 3 is 30. 30 plus 48 is 78. Plus 0 is 0. Plus 0 is 0. Wait, 78 plus 0 is 78. And then 78 plus 0 is still 78. And then finally, 10 times 1 is 10. 10 minus 56 is minus 46. Plus 0 is still minus 46. Plus 6 is minus 40. Now, hopefully I didn't make any mistakes there. I'll go back after I make the video and check that this was right. And I'll have to edit it if it was wrong. But hopefully that gives you a sense for how to multiply these things. And again, what I'm doing here is not magic. I've had to do all the same calculations that you would do if you did it in this kind of column by column vector multiplication way that 3 blue, 1 brown presents. And the nice thing about that presentation is it really explains what's going on, why you're doing this. It's the justification for why these things are linear transformations. I like this approach where we set the matrices up like this because visually it's very clear which column and row we're using to get an entry. And it breaks our computation down into small computations so that we're doing them one at a time and we're less likely to make mistakes. And if we make mistakes, it'll probably just be in a single entry. They'll be easier to fix. Okay, so I wanted to go back and just really quickly, and this is the part where if you don't want to hear kind of the why this works, feel free to stop the video if you were just looking for a little more reinforcement on multiplying matrices. Why does this work? That is, why is it that this multiplication is telling us where linear transformations, or where the composition of two linear transformations takes a vector? Why is matrix multiplication composition of linear transformations? And just really quickly, if we look at the two matrices that we're working with here, this matrix corresponds to a linear transformation from, well, the dimension of the input is the number of columns, so from R2, and the output is the number of rows. So this corresponds to a linear transformation from R2 to R4. This matrix, in a similar way, and pause if you want to think about this for yourself or think about it while I'm writing, this corresponds to a linear transformation from R4 to R3. And this is something that we write this stuff backwards. Someone somewhere made a horrible mistake, or probably a lot of people made a horrible mistake. When we write this matrix multiplication, we're saying do this transformation first, then this one. The 3 blue, 1 brown video talks about this. And the same is true when we write composition of functions, right? So if I'm thinking of this as the linear transformation t, and this is the linear transformation s, then this product is s composed with t. But when I write s composed with t of a vector, that means s of t of v, which is saying do t first, apply t, and then apply s. So s composed with t, if you just read it and don't think about it, you might think this is saying s then t. It's actually saying t then s. And so what's the mistake? Because we read left to right, really we should be writing this vector over here, right? This notation would be a lot better if the vector were written on the left. So that it would be, we start with the input, and then we apply this thing, and then we apply that thing. And then we would have to change how we defined matrix multiplication times vectors. We would have to write our vectors as row vectors. It's not really important. The point is that if it seems backwards, it is backwards. You're not crazy. Someone made a bad decision at some point, right? If we're reading left to right, we should not be writing composition of functions the way that we do, but we're stuck with it. It's the convention, and there's nothing we can do about it. This goes against a lot of what happens in this course, where everything works nicely and things are defined the way they are for a reason. This is defined the way it is for a bad reason, or no reason. Okay, so back to the point. What's going on here? So we have a linear transformation from R2 to R4, and so we can take vectors in R2, send them to R4, and then take those vectors in R4 and send them to R3. And we're saying that this is the same as just starting by taking a vector in R2 and sending it to R3. So the first thing to notice is that the dimensions do line up, right? That is, our product of two matrices does give us a matrix of the right dimensions to be a transformation from R2 to R3. But why does it work? The whole point is that this linear transformation here, it sends the first standard basis vector, 1, 0, to this vector. And then this linear transformation then sends this vector to whatever you get by multiplying this vector times this matrix vector multiplication. And if you follow that process, I'm not going to write it all out, you get this. So in other words, when we start with the standard basis vector, apply this transformation by matrix vector multiplication, take the corresponding vector and apply matrix vector multiplication to this is what we get. And similarly, if we start with the second standard basis vector and push it through that process, we get this thing. And that's what it means to be the matrix of a linear transformation. So if you follow through with how this works, you realize that this is the only way that we could define matrix multiplication so that it lined up with composition. If you want a more in-depth explanation of that, the textbook has kind of some more in-depth stuff. I don't think it's that useful of a thing to overly dwell on. That is to focus too much on the calculations. What's important is that you see the big picture, that matrix multiplication is composition of linear transformations. And they mentioned this in 3 Blue, 1 Brown. If you're trying to prove something like associativity is the classic example, trying to figure out why this is true by using the process of matrix multiplication is impossible, or not impossible. It's very ugly and computationally intensive. But if you think of this in terms of transformations, this is just very straightforward to show because of the way that composition of functions is defined. So this connection between linear transformations and matrix multiplication, it's less important that you can, prove that it works. What's more important is that you understand that it's true and you understand the implications of it.